So if we extend our problem to a 2D problem, okay, we basically now have a two-dimensional computational domain instead of a 1D. So when we did 1D, we had only this this I index going from 1 to n, but now we also have a j index, that guy, going from 1 to n. Okay, and I have made it kind of arbitrary, saying that okay, I have an arbitrary length L and an arbitrary height h. Okay, they don't have to be equal. Also, n and m doesn't have to be equal. Okay, so this is like a wireframe, and you know the elements are pretty easy to number. And as we mentioned, that's the beauty of a structured mesh. You have IJK ordering, so you know exactly where you are when given a certain index. Okay, our nodes are all located at the junction of these horizontal and vertical lines. Okay, I haven't drawn them explicitly, but you know that. So following what we did for 1D, we had delta x. Again, we are using equal spacing of the mesh so that our derivation stays simple enough. We had delta x equal to L over n minus 1. Now we have delta y equal to h divided by m minus 1. Again, y m minus 1 because we have m spacings in the vertical direction. Okay. Governing equation is now the Poisson equation, not 1D but 2D. You have, it's a partial differential equation now, no longer an ordinary differential equation, because phi is now a function of both x and y. Okay. Later on we will move to problems where phi will be a function of time x and y, so unsteady problems. Right now we're still focusing on steady state problems. Okay. All right, so our objective, again, just like before, is to derive a set of algebraic equations for all the nodes. Okay. In this case, we have n times m unknowns. As you can see, the last node is n comma m. But really, if you think about it, if I have a 10 by 10 mesh and I count the number of nodes, that's the 100th node. Okay. So the total number of unknowns is n times m. One common mistake I often see students make is I go through the lecture and then I ask them to write a program. They allocate a coefficient matrix which is n times m. No, the coefficient matrix is n times m, comma n times m. Okay, n times m is the total number of unknowns. So don't allocate memory for the coefficient matrix which is n comma m. That's totally wrong. Okay. So if I have 10 nodes in the x direction, 20 in the y direction, your coefficient matrix will be 200 times 200, not 10 comma 20. Okay. All right. So that's our number of unknowns, which we are going to denote by a capital K from this point onwards, n times n. Okay. Now, when we set up a matrix, let's say we do a finite difference of this equation and we come up with our discrete equations and we want to set up the matrix. Okay, that matrix should be set up in such a way that I have this unknown vector which goes from phi 1 through phi capital K. Okay, so if let me give you an example here. Okay, so if I have just, let's say, a 3 by 3 mesh with nodes here. Okay, this is 1 comma 1, this is 1 comma 2, this is 2 comma 2, and so on. This is 3 comma 3. Okay, now I can't use this I and j index anymore when I set up the matrix. Why? Because what I need to do is I have 9 unknowns. My unknowns will be phi 1, phi 2, all the way up to phi 9. Okay. Notice that I am not calling it phi 1 comma 1, phi 1 comma 2, phi 1 comma 3, because if I keep using that double notation, my computer won't understand anything. It thinks of this as a one-dimensional vector which has 9 unknowns. Okay. Similarly, the coefficient matrix here will have A1, 1, A1, 2, A1, 3, and so on. Okay? This comma here is not the same as that comma there. This is simply saying how node number 1 connects to node number 1. How node number 1 connects to node number 2. Okay? So this, if I take one row, remember I said that a row represents one finite difference equation. Okay? So this is basically saying that there will be 9 elements here corresponding to the 9 elements here. So I will have, so this last one will actually be A1, 9. Okay? So this guy will multiply phi1, this guy will multiply phi2, this guy will multiply phi3, and so on. Okay? So the point I'm trying to make is that when you set up the matrix, you can't use the I, j index anymore. You have to convert each of the nodes to a unique number. Okay, not 1, 2, but you have to say, okay, this is node number 5, and this is my unknown number 5. Okay, if I go here, I'm going to say, okay, that's my node number 5 or 6 or whatever it is, and therefore that's phi 6, not phi 2, 2. Okay, everybody understand that? Otherwise, you're going to get a sort of a 3-dimensional matrix. All right. Okay, so how do we do that? Convert the double index to a single index. You can do it any number of ways. What I have shown here is, okay, I need to switch this. What I have shown here is just one way. So for example, I could number the nodes 1, 2, 3, 4 along this direction, okay, and then this is node number n, and then I go back, and then this becomes n plus 1, n plus 2, n plus 3 up to 2n, and then I get 2n plus 1, 2n plus 2, and so on. Okay, that's just one numbering pattern. I could have numbered it differently. I could have gone 1, 2, 3, 4 in the vertical direction, 1, 2, 3, 4 up to m, and then I could have come back here and said this is m plus 1, m plus 2, m plus 3, and so on. Okay, any way you choose, you can number it. But at the end of the day, they must have a unique number. And that's the unknown number that you're solving for. Okay, so if I have a 10 by 10 mesh, you'll have 100 unknowns. Each unknown will have, corresponds to a specific node and has a unique number. Okay, later on, when you want to plot it, let's say you want to do a contour plot and you want to go back to your I and j, you can do the reverse transformation and convert all these node numbers back to the ij index and then plot it. Okay, if that's something you desire. But you can't work in a matrix setting, you can't work with the ij index anymore. Okay, it has to be a unique index. So if I follow the numbering pattern that I have shown here, okay, this is the formula one could use. So if my unique node number is k, then I can combine the I and j index and say k is equal to j minus 1 times n plus I. Okay, now if you do a thought experiment, you find that, okay, if j is equal to 1, that's this very first bottom row. Okay, notice that j equal to 1 is that guy there. Okay, so if j is equal to 1, then the first part of that formula disappears and k becomes equal to I, which is exactly what you have. This is 1, 2, 3, 4. So the very first row, the I index and the k index is identical. When j becomes 2, you jump up to that row. Okay, and now you get 2 minus 1 times n, which is n, plus I. Okay, that's what you get here, n plus 1, n plus 2, and so on. All right, and so on. It continues. You get 2n plus 1, 2n plus 2 in the next row, and so on. Everybody understand this? So this numbering pattern that I've drawn here is consistent with this formula I'm using to convert the I and j index to a unique index k. Okay? Yeah.
Do they have to be sequential numbers?
Okay, let me repeat the question for everybody's benefit. He asked, do they have to be sequential numbers? That's a good question. The answer to that is in the end, if you rely on that numbering to develop a solver, then yes, you should number it in a sequential way. Okay? If not, if you're writing an unstructured solver for this problem, then you can number it any way you want. Okay? It doesn't matter. But then you need to also store what number is connected to what other number. Okay? And that brings us back to this stencil here that I've drawn. Okay? The way I'm numbering it, even in terms of the k index, the nodes get automatically numbered. Okay, for example, since I'm going from left to right, okay, if this is node number k, this is automatically k plus 1, this is k minus 1. Okay, so I'm going to go all the way here and then turn back and go this way. So by the time I get to the node which is on the north side, that has been displaced by n nodes. So that becomes automatically k plus n. Okay, and similarly the one on the bottom is k minus n. Okay, if I did not number it sequentially, which is the point that you raised, then I wouldn't have that stencil. I wouldn't know whether that's k plus 1 on k plus n on top or what it is.
Okay. I was thinking that you could just take that index like 1, 1, 2, 2 and make it into a single number. So then you have 11.
Which is what we are doing here. See, we have the I and the j. We are converting that to a k. Okay, so the fact that we are using a formula to do it automatically makes it sequential. It can be random. Any other questions, comments on that? Everybody understand this? So all we are doing is renumbering the node, converting a two-dimensional numbering pattern to a one-dimensional numbering pattern. That's all we're doing. Okay. All right, so this is, let's see, this is how my stencil is now going to look like in terms of the global index. Instead of I plus 1, I minus 1, j plus 1, j minus 1, we have a k, where on the left and right we have k minus 1, k plus 1, and then on the top we have k plus n and k minus n. Okay. So the next thing is to develop a finite difference approximation, obviously, for our derivatives. So if this is our stencil, then this part we had already derived in class. This guy. Okay, we know that d square phi dx square is that plus an error of second order accuracy. Similarly, we can do a Taylor series expansion in the y direction, and we are going to get that. Okay. Now, one thing I do want to emphasize here is that this is possible because these mesh lines are Cartesian, perfectly perpendicular to each other. Okay. If, let's say, my north was here and my east was here, then if you do a Taylor series expansion of phi, you got to do x plus delta x comma y plus delta y. It's a two-dimensional Taylor series expansion then, automatically. What has happened by virtue of the fact that east is exactly on the same x line as naught is that delta y is 0. So even though you do a two-dimensional Taylor series expansion, all the y derivatives have dropped out because delta y is 0. So essentially it reduces to a one-dimensional Taylor series expansion, and you get back these expressions. Okay. If you didn't have that, if you had a double Taylor series expansion, you would also get these types of terms. Okay. So that's something to keep in mind, that these finite difference equations we are writing down here is really only valid for a Cartesian mesh. If you don't have a Cartesian mesh, then you got to do coordinate transformation, which is what we had talked about earlier. Okay, remember I had talked about the fact that when you do coordinate transformation, the d square phi dx square plus d square phi dy square is not going to give you back d square phi d xi square plus d square phi d eta square. There will be cross derivatives. Okay, and that's the reason. Okay. Now one might say, well, you know, if there's such a big restriction, why do we even bother about that? The point is, right now we are trying to keep things simple so that we can learn how to set up these equations, how to solve them, and so forth. Later on, we will be doing unstructured meshes and so forth already, which will handle all these issues anyway. Okay? Any questions? Okay, so when we put our equation together, this is what we get. Our governing equation now has 5 terms instead of 3. Okay, and in terms of the global indices that we defined, the k index which combined the I and j, we have that kind of a formula. Notice that the x derivative has k plus 1, k minus 1, the y derivative has k plus n and k minus n. Okay, any questions? And I could write it in a form where, you know, all the terms have been pulled together, so you clearly see there are 5 terms. This is your diagonal right there, right here. Okay, and then this is the eastern node, the western node, the northern node, or sorry, the southern node, the northern node. Those are your coefficients. Okay, up to now you've been solving one-dimensional problems where you didn't have these 2 terms, but now they have shown up, the k plus n and the k minus n. Okay, in general I could also write this in the matrix form, which is what I was showing you here, that you could have A11 times phi1, A12 times phi2, and so on in that form. Okay, so that's the same as writing it if I have a generic. So suppose I have a phi k right here. Okay, so the one before it will be phi k minus 1, the one after it will be phi k plus 1. Okay, and then there will be a big gap. We will have phi k plus n. By gap I mean there will be other numbers, but those are not relevant. And then here for the coefficient matrix you will have, right here will be a k comma k, then you will have a k comma k plus 1, then you will have a k comma k minus 1. Okay, and then there will be a bunch of zeros here, and then finally here you will have a k comma k minus n and a k comma k plus n. Okay, and then again zeros beyond that. So what's happening here is, if you look at the multiplication, phi k minus n gets multiplied with a. So you start at the very top. There are other variables here. So for example, phi1 will get multiplied with a 0, phi2 will get multiplied with a 0, and so on. You get to phi k minus n, that gets multiplied by that coefficient. Then you go to phi k minus 1, that gets multiplied by that guy. Okay, phi k times a k k, phi k plus 1 times a k comma k plus 1, and then that guy times that guy. Notice that this variable and that variable, they are spaced apart by n nodes, okay, or n elements. Same thing here, they are spaced apart by n elements. Okay, if you look at the this row here, same thing here. These 2 guys are spaced apart by n, and these 2 guys are spaced apart by n. Okay, everybody understand the structure of the matrix? The rest are all zeros. Okay, now boundary conditions are going to come into play, but we'll talk about that later. So let me go back to what I had up on the screen here on the computer. So that's the structure that I was just describing. So here's your diagonal, okay, and then you have all the 5 off diagonals, or sorry, 4 off diagonals for the 4 nodes that are surrounding the node that you're developing your equation for. All right, any questions? Okay, so when I write out the matrix, that's what it's going to look like. What you will see is 3 diagonals. It's kind of hard to see here because the spacing gets messed up when you put it in a computer, but there are 3 diagonals here clustered together. Okay, and then there are 2 other diagonals which are a little bit far away. Notice these dots I've put, there are all zeros there. Okay, everywhere else these are all zeros. So just 5 bands. 5 bands, but the 3 center ones are clustered together. The other 2 are not together. They are spaced far apart by n elements from the center. Okay. Now, in the math or numerical methods literature, we talk about tridiagonal solvers. We've talked about that already. We had only 3 diagonals clustered in the middle. Some people talk about pentadiagonal solvers, but this matrix that you have here, this is not called a pentadiagonal matrix. Okay, when people say pentadiagonal solver, they usually refer to 5 diagonals clustered in the middle, which is different from 5 diagonals where 2 of them are far away. Okay, and the reason for that is if you did a Gaussian elimination with this guy, you will find that all the zeros on the top half have become non-zeros by the time you finish the forward elimination step. Even though right now there are only 4 diagonals on the top half, or 3 diagonals rather. Okay, that's the difficulty with these kinds of matrices. If the diagonals were really clustered in the middle, you wouldn't get that. Okay, you would still get sparse matrices to work with, but unfortunately with this kind of a scenario you don't get that. Okay, everybody understand the matrix structure here? So as long as we have IJK ordered mesh, structured mesh like we had, we are always going to get these banded matrices. Okay, for 2D we are going to get 5 bands, for 3D we are going to get 7 bands. There will be 2 others showing up. Okay, for 1D we had just 3 bands, but these are banded matrices. If the mesh is unstructured, what's going to happen is you're not going to get a banded matrix anymore. You're still going to get a sparse matrix, because what happens is every node will talk with only 4 or 5 other nodes around it, not with anything else. So what that means is every row here is going to have a total number of elements that equals the number of nodes you have in the stencil. Okay, so right now we have 5 points in the stencil. That's why we get 5 elements. Everything else is 0, right? If you had an unstructured mesh and let's say one node is surrounded by 7 other nodes, okay, you would get 8 non-zero elements in your whole row. Everything else will be 0. Because the fact that they are all zeros, the others are all zeros, that means that this node is not talking to any other node, is not communicating with any other node. Okay? That's what these mean. So that's why these coefficients in the matrix are often called link coefficients. Okay, this is a term that I'm going to be, well, let me write it here one more time. They are called link coefficients. Okay, why? Because they link one node to another. They are basically your method of communication between one node and another. Okay, if I have a node here and another node there which is outside of the stencil I'm considering, then the link coefficient between this node and that node far away is 0. It's not communicating. Okay, that's why the link coefficient is 0. It's not linked to that node. All right. The ones that are surrounding it are the only ones that are linked to it. Okay, and this has to do with, if you think about it, this has to do with physics also, because when we talk about solving PDEs, we are really trying to represent physics. So suppose you have heat conduction. Okay, I have a point here. That point is going to be influenced by the temperature of all the surrounding nodes. It's not going to be influenced by something which is 1 mile away. Okay, that's the physics of conduction. And that's what your equations give you, really. Okay, there are certain other kinds of physics where that's not true. For example, when you have radiative transport. Okay, I mean, we have interaction with the sun, which is millions of miles away. Okay, so if you solve a radiative transfer problem, you will find that this matrix is completely full. There are no zeros at all, because everything is talking to everything else. And that will come out of the equation, the radiative transport equation. When you look at it, you will see that actually. That it's not a local phenomena that we are looking at. Okay? But these diffusion operators, for example, that we look at, so this d square phi dx square plus d square phi dy square, we often call that a diffusion operator because it represents a diffusion process in physics. Okay? When we have something like that, we always see these sparse matrices. Okay? Any questions? All right, so yeah.
So for something like Gauss-Seidel line solver for unstructured mesh, your stencil would be changing for each node, right? Because some nodes might have 5 neighboring spaces, others might have 9.
Yeah, sure. So what that means is that a certain, let me just wipe this. One row may have 5 elements, this row may have 8 elements. It's perfectly okay. Nothing wrong with that. And that's why you don't get a banded system anymore for unstructured mesh. If you have a structured mesh, you can't have 5 for some and 8 for some. By definition, they'll all have the same. Okay. Any other questions? Okay. So I talked about this already, that the matrix will be strongly sparse as long as we have these kinds of diffusion operators, because the node in question is only affected by its nearest neighbors. Okay? So this is the general structure. Okay? Here I've just drawn a schematic. So you can see there are 3 bands clustered in the middle, and then 2 bands far away, and in between we have a bunch of zeros. Okay? That's what our coefficient matrix A is going to look like. And this is our unknown vector which we are trying to solve for. And this is our right-hand side. The right-hand side may have a source term. It may have other terms that show up from boundary conditions, like we got when we did Neumann and Robin boundary conditions for 1D. Okay? So ultimately, our job is to solve this system of equations. Okay? I already mentioned this, that the north and south diagonals, these two guys, this is the north diagonal, this is the south diagonal. This one is the east, this one is the west, and this one is the central diagonal. Okay, so those diagonals represent contributions of the various nodes. So the north and south are moved far away, and as I said, the total number of unknowns, this guy here and this guy here, they are of size k, which is equal to n times m. And this guy, this matrix here, is of size k by k, k being n times n. Okay? Okay, any questions? Okay, now this is something we have talked about. I'll just quickly go through this because we've discussed this. First of all, the matrix size is k squared. Okay, that's how many real numbers you have to store. All right, of which only 5k, in fact not even 5k, because all the diagonals are not k elements long. Some of them are shorter actually. Okay, but let's just say they're all k elements long. So out of those, only 5k are non-zeros. Everything else are zeros. Okay. Now in a direct solution, we talked about this already. You have a forward elimination step and a backward substitution step. So I'm not going to go over this in great details here. And the problems you run into are memory. I gave you this example in the last class where, let's say you have, so your matrix is k by k, and k, let's say, is 100 by 100 mesh. Okay, so n is 100, m is 100. It's a pretty simple problem, 100 by 100 mesh in 2D. Okay, so that gives you 10 to the power 4 unknowns, which is not much. All right, that means your matrix needs to store 10 to the power 8 real numbers. If you take 8 bytes for each number in double precision, then you have 800 megabytes of memory requirement. Okay, which is not trivial at all for a 100 by 100 mesh problem If you go to 3D, if you go 100 by 100 by 100, 1 million, then that's it. Can't solve it. Okay, that's one big problem, memory. Unfortunately, or we should really make use of the fact that only those many non-zeros are in the matrix. So really, we are wasting a lot of memory. Okay, because we're starting with 5k non-zeros, but we are allocating memory for k square real numbers. Okay, it's important to understand that computers don't distinguish between a zero and a non-zero. To it, everything is a real number. Okay, in our brain, it's easy to recognize, okay, this is a zero, this is a non-zero, and therefore all the groundwork should be done by our brain rather than the computer having to deal with that. If we know that certain numbers are zero, we should develop an algorithm that capitalizes upon that rather than have the computer do that, because the computer will not even recognize this is a zero versus a non-zero. In fact, sometimes a zero in a computer is stored as a very small number, 10 to the power minus 236. Okay? But it doesn't understand that's a zero. All right? The other problem is, as I mentioned, the computational time, and this is really the bigger of the two problems, because, as we said, the forward elimination, the number of floating point operations, long operations, multiplication and division, scale as the number of unknowns cubed. Okay? And that's a big problem. That simply means that if I increase my problem size by a factor of 10, normally I would expect, okay, size of the problem has gone up by a factor of 10, so I should have to do 10 times more work. Okay? I mean, we all talk about unitary method from our early childhood. Remember those problems where they used to say, okay, 5 people build a house working 3 hours a day in 2 days. How much time will it take 10 people to build the same house working 5 hours a day? Okay? These unitary method problems. If we apply that here, it doesn't work because the computational effort scales nonlinearly. Okay, so something that problem size, if it goes up by a factor of 10, computational time will go up by a factor of 1,000, which is really a big problem. Imagine something you were calculating in 10 minutes, and now all of a sudden it's taking 1,000 minutes. 1,000 minutes is not a joke. It's a lot of time. Okay, so that's really the big issue that we encounter, that we cannot use direct solvers. Typically, Gaussian elimination is not used for scientific calculations beyond about 100 unknowns. Okay, it's prohibitive, and that leads us to so-called iterative solvers. Okay, so this is what we are going to be talking about for a long time in